Okay. Başlıyorum o zaman. Okay, welcome. Welcome to the International Conference on Advanced Material Science and Engineering and High-Tech Applications. So I'm going to be chairing the session in Ankara. So we have the keynote speaker. The first speaker is Tagashi Omatsu. He's from Chiba University, and he's the director of Molecular Chiralities Research Center. He was awarded, let me talk about his CV a little bit. So he was awarded the PhD degree of Applied Physics from University of Tokyo. He has contributions to a research field of photonics and optical sciences, and he has more than 200 papers in his field, and he has more than 3,000 citations in his field. So I'd like to welcome Professor Tagashi Omatsu from Chiba University. Let me tell you our audience first that this seminar will be live broadcasted on YouTube, and it will be also recorded on the Zoom channel. Okay, so let me start the presentation of the first speaker, Tagashi Omatsu, and I will start his recorded video now.
Sayın hocam,
Telefona bakar mısın?
sayın hocam.
Buyurun.
Hocam görüntüyü açtıktan sonra kulaklıkla değil de dış sesle mikrofona verebilir misiniz sesi mümkünse?
Video kesildi mi?
Evet hocam, video kesildi.
Bir dakika. Tekrar başlatıyorum da.
Dış
Bir
sesle
dakika.
hocam, dış sesle kulaklığınızdan değil de dış sesle kendisinin almasına izin verin.
Dış
Yani sizin
sesim.
mikrofonunuzdan açtın. Ses mikrofonunuzdan gelsin.
Peki tamam. Kulaklığı çıkarayım yani.
Evet.
Evet sayın hocam.
Such a merited matter of soliton matter can be considered some microscale matter. Can receive.
Görüntüyü baştan paylaşmanız gerekiyor. Sıfırdan başlatın isterseniz, tekrardan başlatın. Daha iyi olur hocam. Zamanımız var zaten.
Bir dakika. Sıkıntı oldu da.
Bir önemli değil sayın hocam. Baştan başlatırsak daha güzel olur. Hem dinleyicilerimiz de daha net duyarlar.
Bir de record şeyine başlayayım da bir dakika. Bir dakika. Şimdi bir de record'a basayım.
Hocam record önemli değil şu anda hocam. YouTube kaydediyor. Siz isterseniz onu hemen halledin sayın hocam.
Tamam,
Sesi girin.
bir dakika.
Ses sunumu açın.
Yapacağım bir dakika. Başlatıyorum şimdi.
Thank you, Gemma. My name is Takashi Omasu-kan from Chiba University. I have a great pleasure to have opportunity to talk about my research work in such a wonderful conference. Unfortunately, I cannot visit Turkey at this moment because of the corona impact. I want to see you in person definitely next time. Okay. Anyway, the title of my talk, Structured Light of ANKARA Materials. At the beginning of my talk, I would like to acknowledge many collaborators, and I would also thank to the financial support GSPS and JST Quest. Key issue of this talk, optical radiation forces. I briefly introduce basic concept for the optical radiation forces. Okay, please imagine the small particle and light comes into such a situation. You know, a part of the light is reflected by the surface of the particle. Okay, a part of the linear momentum of the light transferred to the particle. Particle must be accelerated. This is the scattering force. If particle has an absorption band of the light field, namely resonance condition, optical field must be absorbed by the particle. Particle must be accelerated well because total linear momentum of the light is transferred to the particle. Okay? In this case, with thinking about absorption force of the light, generally speaking, scattering force and absorption force can be written by following expression, namely is proportional to the time average Poynting vector of the light. Of course, optical field is electromagnetic field. Particle is polarized. Polarized particle can be trapped by the optical field by the Lorentz effect. Okay? This is a gradient force. Can be written by following expression. Anyway, scattering force, absorption force, gradient force, generally speaking, is quite tiny. Typically, because Newton level, of course, human body doesn't have any photon radiation pressure from the optical field. But small particle, for example, metal particle with a micrometer scale, mass 10 to minus 14 kilogram or something like that. This particle can be accelerated well by photon radiation pressure. Okay, such optical radiation force, very attractive for the medical application at this moment. So optical manipulation proposed by Professor Ashkin. He is Nobel Prize winner in 2018 in physics. Okay. to 30 years. Okay, 1992. Orbital angular momentum light. Laguerre-Goussian mode carried such orbital angular momentum light. Professor Allen proposed theoretically such existence of the orbital angular momentum light. Okay. After huge number of the researchers have credited about the existence of the orbital angular momentum of the light and Laguerre-Goussian mode. Okay. I would like to mention briefly Laguerre-Goussian mode. Okay. Laguerre-Goussian mode, eigenfunction of the para-axial electromagnetic radiation like that. Okay. It exhibits polynomial, Laguerre-Gaussian polynomial on azimuthal phase I and phi. Okay. Typically, this Laguerre-Gaussian mode exhibits diffraction effect on annular intensity profile. Okay. Such a Laguerre-Gaussian mode can be created by spiral wave plate like that. We also have another kind of the orbital angular momentum lights, Bessel beam. Bessel beam is an eigenfunction of the space separated variance equation, you know. The Bessel beam can be written by following expression as the mutual component, radial component, and propagation component independently. Okay? It exhibits non-diffraction effect, namely the rate of wave propagating inside space. But at the mutual phase and radial amplitude doesn't change. Okay? It exhibits typically multiple ring profile with central dark hole. So Laguerre-Gaussian mode can be converted by the axial lens into the Bessel beam. Okay? Such a Laguerre-Gaussian mode, Bessel mode, carry the orbital angular momentum determined by this azimuthal phase component. We want to say optical vortex. Okay? How to understand basic concept of the optical vortex with orbital angular momentum light? Quite simple. Please imagine such a helical light. Okay? In this case, pointing vector of the light is inclined to the propagation direction. Okay? A part of the scattering force exists cross section of the laser beam. This is orbital angular momentum light. And this must be the winding number of helical wavefronts come from the periodic boundary condition in symmetrical coordinate. Okay? This L is a quantum number, generally speaking. We say topological charge. And the helical wavefront has on-axis phase singularity, namely the optical vortex always has central dark hole. Okay? We also must mention about the handiness of the optical vortex, like handed optical vortex exists. This handiness determined by the twisted direction of the wavefronts. Okay? Clockwise and anti-clockwise direction. I would like to summarize property of the optical vortex. Optical vortex exhibits handiness, orbital angular momentum, eigenspace, and annular intensity profile. Okay? This is a good movie of the interaction between the particle and optical vortex. You can see the particle rotate to the clockwise direction. This is the orbital angular momentum effect. Size of the particle 500 nanometers is water cell. Okay? Orbital angular momentum can drive the orbital motion of the small particle with some micron scale. How to use such as orbital angular momentum light optical vortex? Okay. most famous application must be the improvement spatial resolution in fluorescence microscope. Generally speaking, spatial resolution of fluorescence microscope determined by pump spot size onto the irradiated target. Okay? Pump spot size typically half micrometer because diffraction effect of the light. Okay? The pumped region radiates fluorescent signal. Fluorescent signal has some micron scale. Okay? In order to break the diffraction limit of the light, we overlay optical vortex on the pump region to suppress fluorescent signal from the target through the stimulated emission or high excitation. So we can expect fluorescent signal just come from central dark hole of the optical vortex. We can significantly improve the spatial resolution of the fluorescent signal up to 20 nanometer scale. This technology is proposed by Professor Stefan Helking at the Planck Institute. They achieve beautiful nanoscale optical microscope image in the biomedical cell. He received Nobel Prize at 2014 in chemistry. Another interesting application must be telecommunication. That, for example, at this moment we are organizing Zoom meeting that many people want to access to the internet. So we must increase data capacity of the telecommunication system. At that moment, if optical vortex, for example, Laguerre-Gaussian mode carry telecommunication data together with the Gaussian mode, we can increase communication data to be doubled, okay? In the free space and inside fiber, okay? Because Laguerre-Gaussian mode is eigenstate. Even propagating inside space, the spatial formation doesn't change. This technology is proposed by Professor Alan Wigner in the University of California, and he is a former president of the USA. Of course, spatial resolution improvement in the microscope and data capacity increasing in the telecommunication system, of course, interesting. But we want to utilize orbital angular momentum light more effectively, So we propose another kind of the application of the optical vortex. We want to say optical vortex material processing. We're thinking about get marriage between the optical vortex and material technology and material science as well. Basic concept is quite simple. We pump the target material by using optical vortex. Surface must be melted and vaporized and softened. Okay? Such a melted matter or softened matter can be considered some micron scale matter. Can receive orbital angular momentum from the light field, start to rotate clockwise and anti-clockwise direction near the surface. They must be recrystallized onto the surface of the matter to form such a helical structure on some micron scale. Such a some micron scale helical matter must be quite useful to develop chiral plasmonic devices, definitely. And such as some micron scale twisted matter quite difficult to be achieved even by utilizing advanced chemical process. Okay? This technology is quite interesting. All fabrication can be performed at room temperature and atmosphere. We don't have to utilize cryogenic and vacuum chamber at all. In the view of cost saving, energy saving, this technology must be quite attractive. First demonstration, 2010, already 10 years back, we found tantalum, and this is metal, by using the optical vortex pulse, nanosecond pulse. this is the same image of the surface of the target, irradiated target. You can find out some small needle-like structure. Here the dark gold target, I would like to show you zoom up image of this tiny needle. Okay? At that moment we can find how this needle is twisted. Okay? Right-handed optical vortex can create right-handed twisted needle. Left-handed optical vortex can create left-handed twisted needle. Okay? That's quite interesting. Orbital angular momentum directly can twist the melted tantalum. Okay? This is a good evidence. Typical size of the needle, 70 nanometer for the cheap diameter. Absolutely some microscope. The pulse spot size of the laser beam is about 30 micrometer, 40 micrometer. And wavelength of the light source is typically 1 micron or 500 nanometer. Okay? We can achieve real nanoscale structure matter. That's quite interesting fabrication. Okay? This must be the magic microfabrication based on optical vortex. Of course, many kinds of the material can be twisted by the optical vortex illumination. Tantalum, copper, silicon, polymer, and gold. All materials twisted. Of course, we can control handles of the structured matter just switching the handles of the optical vortex. Okay? Quite simple technology. Very interesting to fabricate new structured devices, including the color fabric material, metal surface, and so on. Okay? In fact, recently many researchers have great interest about such microfabrication based on the optical vortex illumination. For example, Russian group, they fabricate silver needle by using optical vortex illumination. Okay? And this is a beautiful demonstration. They can create such as some micron scale structured matter onto the silver substrate. Okay? And another research group, Ottawa University, they can fabricate silicon needle by deposition femtosecond vortex pulse. The structure is quite beautiful, okay, and surface has no debris at all. This is a femtosecond laser effect, And this is Japanese group. They fabricate needle onto the surface of the multi-layer material by deposition of thin X-ray vortex pulse with femtosecond pulse duration. It is also quite interesting topic. And also many perform twisted needle array onto the material, okay, by using the holographic technique. Anyway, many researchers have great interest about such microfabrication based on optical vortex at this moment. Okay? We're thinking about another new direction. We want to propose new direction of application of optical vortex at that moment. So microfabrication technique based on optical vortex material processing, just we want to control morphology of the surface of the matter. Okay? We want to create much macro scale twisted structured matter by optical vortex illumination. First thinking about what is a game changer. Okay? At this moment, we want to propose new technology, twisted spatial soliton effect by optical vortex illumination beyond chiral surface structures. Okay? Key component, photopolymerization effect. Okay? And printing technology based on the I would like to show second demonstration. which is better? It is also quite interesting topic. And also many perform twisted needle array onto the okay, by using the holographic technique. Anyway, many researchers have great interest about such microfabrication based on the optical vortex at this moment. Okay, we're thinking about another new direction. We want to propose new direction of the application of optical vortex at that moment. So microfabrication technique based on the optical vortex material processing. Just we want to control morphology of the surface of the matter. Okay, we want to create much macro scale twisted structures matter by optical vortex illumination. First thinking about what is a game changer. Okay, at this moment we want to propose new technology, twisted spatial soliton effect by the optical vortex illumination beyond chiral surface structures. Okay, key component photopolymerization effect. Okay, and printing technology based on the spin jet. I would like to show a second demonstration. Key issue must be the photopolymerization effect by irradiation of the UV light or visible light. Okay, at that moment, photoinitiator become activated photoinitiator attack monomer and oligomer to encourage cross-linked polymerization inside the QR regime, liquid phase QR regime. Okay. By using this effect, we can fabricate fiber. Basic concept is quite simple. Laser beam tightly focus onto liquid phase QR regime. Okay? Near the focus spot, polymerized matter is created. Such a polymerized matter has relatively higher refractive index rather than liquid phase QR regime. Optical field, irradiate optical field is confined inside polymerized matter, namely the polymerized matter works as waveguide of the optical field, okay, to compensate diffraction effect of the optical field. This must be the spatial soliton effect, okay. Optical field confines small area inside QR regime. Okay, induce photopolymerization significantly. After that we can fabricate fiber. We want to say this is a self-writing waveguide effect. Okay, just let the beam inject inside QR regime, we can fabricate fiber. Okay, at that moment we want to apply optical vortex to this technology. What happens? Now we can expect orbital angular momentum can twist fabricated fiber like that. Helical fiber must be created. Okay? This is 2-1. We perform the experiment. At that moment, how to fabricate long-scale helical fiber? So wavelength of the light source is quite important. We prepare this material NOA63. This is the absorption band of the NOA63. UV light visible light, which is better. Okay? In order to reduce absorption loss inside material, we decided to use 532 nanometer visible light. Okay, this wavelength corresponds to the cut-off value of the absorption band of the material itself, QR regime itself. Okay? We expect significant reduction of the absorption loss inside the material. Okay? According to the Rayleigh scattering theory, we also can reduce scattering loss inside the material. Namely, the by utilizing the visible light, okay, we can reduce significantly absorption loss, scattering loss as well. And we have another question, which is better, Laguerre-Gaussian mode and Bessel mode? I previously mentioned that we have two kinds of the optical vortex, okay? Laguerre-Gaussian mode, Bessel mode. Laguerre-Gaussian mode exhibits diffraction effect like that. Bessel beam, this is the eigenfunction in the electromagnetic equation. So radial coordinate and mutual coordinate, propagation coordinate separate away. Okay? It exhibits non-diffraction effect. Which is better for microfabrication? Tightly focusing is better, or non-diffraction is better? This is a big question. Okay? Laguerre-Gaussian mode and Bessel mode can be converted with each other. For example, Laguerre-Gaussian mode can be converted to Bessel beam by using optical lens. Quite simple. We compare the performance of microfabrication between the Laguerre-Gaussian mode and Bessel mode. Okay. Experimental setup is quite simple. We create optical vortex by using the spiral phase plates. At that moment, laser wavelength 532 nanometer green laser. Laser power is about 1 watt. The created optical vortex focus on the inside cell, including liquid phase regime. Okay? Transmitted light observed by the CCD camera and photopolymerization effect is also observed by the CCD camera from side view. Thickness of the regime is about 1 centimeter typically. Laguerre-Gaussian mode donut beam profile injected inside the regime. Okay, the confocal length of the Laguerre-Gaussian mode inside regime is about 1 millimeter. This is the diffraction effect. Okay. In order to convert the Laguerre-Gaussian mode into the Bessel beam, we introduce optical heat. Experimental setup, absolutely the same, just introduction, the optical heat, At that moment, Bessel beam with multiple ring profile injected inside regime. Of course, Bessel beam exhibits non-diffraction effect. Confocal length, roughly couple millimeter extended. Okay? Which is better? I would like to show you experiment. The result. This is a movie of the side view inside regime. This is the top view, namely the spatial form of transmitted light. Okay? At first, I would like to show you the Laguerre-Gaussian mode case. The laser beam comes into from left to the right. Okay? Fiber is created. At the same time, transmitted light is distorted significantly. Okay? In fact, length of the fiber is limited up to 1 millimeter or 2 millimeter or something. Okay. In the case of the Bessel beam, laser beam comes into the cell. Fiber is created. And spatial form always multiple ring. And you can find out this multiple ring is rotated clockwise direction. This rotation of the transmitted light means fiber is twisted. Okay? The good evidence of the helical fiber formation inside the regime. And this is quite important. Even after fabrication of the fiber, transmitted light still multiple length, namely the Bessel beam can propagate inside the fiber safely, Effective length of the fiber reach up to the 1 centimeter. I would like to show you optical microscope image of the fabricated fiber like that. Beautiful fiber is created. Typical diameter of the fiber is about 3 microns. Length of the fiber over 1 centimeter, typically 1.5 centimeter. Okay? Maximum value is 1.5 centimeter. That corresponds to the thickness of the cell, you know. Quite long scale fiber must be fabricated. This is a magnified image of the part of the fiber. You can find out this fiber is twisted well. Okay? Such a helical fiber creation must be breakthrough for the microfabrication technique, definitely. Such a fabrication of the helical formation can be understood by numerical estimation based on the nonlinear Schrödinger equation. Okay? This helical fiber formation one kind of spatial fluid of the light field. You know, the numerical estimation can support well experimental result. So I would like to mention about the application of the fabricated fiber, you know, how to utilize. For example, one device, two devices, we want to connect between them. At that moment, Bessel beam comes into, okay? And fiber is created. And we can connect two devices by the helical fiber. Okay? Such a device based on, for example, the OM mode, the orbital angular optical vortex mode, the multiplexing telecommunication system, for example, you know, we can utilize such a connecting devices. Okay? Must be quite important for telecommunication system and so on. Now I have another 10 minutes. I want to show you another demonstration based on the optical vortex. We want to apply optical vortex to laser ins or transfer. This technique we want to say lift. Lift is quite attractive. Okay, that can be applied to fabricate 2D patterning onto the receiver. Basic concept is quite simple. Donor film. Here, we found this donor film from the back side by using laser powers. Donor film is broken into the fragment, and the fragment fly away and captured by the receiver. Okay? This is a movie of the lift. The donor fragment captured by the receiver. You know, this technology must be useful for the micro-patterning of organic material or 2D material and so on. But unfortunately, we cannot control the size of the fragment. Okay, typically difficult to achieve high spatial resolution. Okay, short flight distance. To overcome such a drawback of the lift, we apply optical vortex to the lift technology. Basic concept is quite simple. We pump the donor film by just optical vortex. Okay? Orbital angular momentum of the optical vortex should transfer from optical field to the matter. Matter must be spinning. Such a spinning motion of the material can stabilize straight flight of the material itself. Okay? We can control flight direction of the donor material. Okay? We should improve the spatial resolution of the micro-patterning. Like that. This concept is two-one. I would like to show you one interesting movie. We prepare high viscous liquid film. Viscosity 4 pascal second. And this is correspond to the honey. like the mayonnaise or something, they are very high viscosity, We pump such a high viscosity liquid by conventional Gaussian wavelength 532 nanometer. Donut broke into many fragments right away. Of course, we cannot control flight of the fragment at all. Instead of the Gaussian beam, we use Laguerre-Gaussian mode. At that moment, Laguerre-Gaussian mode, quite interesting, can create blister, create jet. This jet is spinning. Okay? Quite interesting. Finally, through the penetrating instability, this jet ejects single droplet. The volume of the single droplet is about picoliter. Okay? Absolutely, performance is the same as inkjet printing technology. Okay? But inkjet printing technology is not available for such high viscous material because of close nozzle coating effect, Such optical vortex induce more transfer, we want to say overlift, can open the door new patterning technology, In fact, at this moment, we can precisely pattern the dot onto the receiver. In this case, viscosity is about 10 pascal second. Okay, very high viscous material. The dot diameter is about typically 50 micrometer, 75 micrometer, or something like that. Of course, we can shrink pattern dot much more, 30 micrometer, 40 micrometer, by just changing the numerical aperture of the objective lens. Okay? We can pattern such a beautiful character onto the receiver substrate. And we also mentioned about this technology must be available for the drug injection or the further micro-patterning, for example, electric devices, so okay. Optical vortex with orbital angular momentum can twist material. Okay, that's quite simple, but such a simple phenomenon can offer many fundamental and applied material science. Okay? For example, helical fiber formation and spin jet patterning technology and so on. Such a technology must be pioneer a new direction of the material science and technology, definitely. We want to say material science based on the optical vortex. Chiral photonics. This is a new twist of the photonics. Okay? Recently published new review article from the Advanced Optical Material and Journal of Nanophotonics. If you have interest about it, please visit the website to download the paper. This is the announcement of the international conference in Japan next year, Optical Meditation and Structured Material Conference. So, of course, topics including the optical vortex and material science as well. If you have interest about that, please visit the website. Website will open very soon. I always want to invite you to the Japan. Now this time, I hope we can organize real meeting in Japan. Okay? So I want to see you there in Japan, definitely next year. Of course, there's such a conference. During the conference, you can enjoy technical science discussion. After technical discussion, I also invite you to Japanese social communication karaoke. I want to sing a song together to be friends, to make the international network. Okay, thank you for your attention. I'll see you in Japan next year. Thank you.
Okay. Let's thank Professor Tagashi Omatsu for his excellent talk. We don't have much time. We exceeded our time limit. So I advise the audience to send their questions through our YouTube channel. In addition, you can also send your questions in person to Professor Tagashi Omatsu. Now, our next speaker is Dr. Nazek El-Atab. She's a research scientist in Department of Electrical Engineering in King Abdullah University of Science and Technology in Saudi Arabia. So she's gonna present the work she has performed with Professor Amar Naife from Khalifa University of Science and Technology. She has worked on nanomaterial-based memory devices. So I'm gonna, she's not with us, I suppose. So I'm gonna share the recorded video of Dr. Nazek El-Atab's video with you through my files. So
Hello everyone, my name is Nazek El-Atab. I'm a research scientist at KAUST in Saudi Arabia, and today I'm going to present the work that I have done under the supervision of Professor Amar Naife when I was at Khalifa University. The work that I will be discussing in this presentation is entitled Nanomaterials and Nanostructure-Based Low-Power Charge-Shuttling Memory Devices. Over the decades, the electronics technology has pushed the limits of our imagination, and we are currently looking forward to major innovations, including autonomous cars, augmented reality, and artificial intelligence. However, these exciting technologies require high-capacity storage, in addition to the ability to transfer the stored data quickly and reliably. Therefore, the continuous progression of memory devices is a very critical technology enabler. In general, memory devices should meet the following criteria. First, they should show a small cost and small area, such that we can integrate a larger number of memory devices, a higher density of memory devices on the same silicon area. Memory devices should be fast enough to allow executing codes directly or accessing the data directly. They should show low voltage and low power consumption. And finally, the memory that stores the information must have a high level of physical security and be extremely difficult to reverse engineer. Currently, there are several types of memory devices that are being manufactured in the memory industry. In specific, in terms of non-volatile memory, they can be divided into two main categories: charge-based and non-charge-based. The charge-based memory devices are basically three-terminal devices similar to a transistor, but with an additional layer for charge storage, and their state, whether programmed or erased, depends on the density of stored charges in this new added layer. The other type of non-volatile memories is the non-charge-based, or the so-called emerging memories. These are very promising and are already being used, but in limited applications. These include the magnetic RAM, where the state of the memory is based on the magnetic moment of the two ferromagnetic layers; the ferroelectric RAM, where the state of the device depends on the polarization state of the ferroelectric capacitor; the phase change RAM uses the resistivity difference between the amorphous and the crystalline states of the material to store the logic state; and finally the resistive RAM, which depends on the resistance of, where the state of the memory depends on the resistance of the dielectric in a metal insulator metal structure. These devices are promising, but they still have several bottlenecks to overcome, including being two-terminal devices, which means that an additional device would be needed to act as a cell selector, and thus this increases the overall area. Some of them use exotic materials, and therefore they are not CMOS compatible. They are expensive. In addition, their reliability is yet to be tested and confirmed. On the other hand, flash memory is the main memory device that is being used, where it covers more than 99% of the applications according to the International Roadmap of Devices and Semiconductors. And this is because of its high reliability. For example, it can sustain the high temperature during the soldering process. It provides a high density, low cost, and maturity of the manufacturing process. The only challenge that flash memory is currently facing, or the main challenge that the flash memory is currently facing, is the scalability. Why do we need to scale down the memory? Well, we need scalability mainly to increase their density so that we can fit and integrate more devices into the same area and reduce the cost per bit and also make them faster. And of course, this is in addition to other benefits such as lowering the operating voltage. To achieve this, two main approaches are specified by the International Roadmap of Devices and Semiconductors. First, using innovative material combinations in the active layers of the memory to enable its scalability without degrading its performance. And this was the focus of my PhD. The other approach is to stack the memory devices in 3D, which allows increasing the density of devices on the same silicon area. And both of these approaches have been specified by the IRDS. Now, other researchers are looking into the other techniques to relax the scaling requirement. Here you can see different scenarios where the logic and memory are integrated together, such as in-memory computing, so that faster computations can be achieved without having to scale down the memory devices. So the main goal here is to minimize the data movement such that more real-time computations can be achieved. In my pre-doctoral research, I have focused on using innovative material combinations, which I'll present in the next slides. Before moving to the different techniques and materials that I have studied, I would like to first explain the operation mechanism of a standard flash memory. So according to the IRDS, the flash memory is used in more than 99% of the applications, including IoT applications and consumer electronic products like smartphones, and this is due to its low cost, high density, wide range of temperature support, and most importantly, a track record of reliability. So how does a flash memory work? A flash memory is a three-terminal device having the same structure as a MOSFET, but with an additional layer embedded within the gate oxide of the transistor, which is called charge trapping layer. The layer in between the channel and the charge trapping layer is called tunnel oxide, while the layer in between the charge trapping layer and the gate is called blocking oxide. The tunnel oxide is usually thin and allows the tunneling of charges during the program erase operation from and to the channel or charge trapping layer, while the blocking oxide is thicker and blocks the leakage of the stored charges to the gate. In order to program the memory, a positive gate voltage is applied so that electrons in the channel gain enough energy and tunnel through the tunnel oxide and get trapped within the charge-shaping layer. As a result, the threshold voltage of the device shifts to the positive side, creating the programmed state. So we can assume that it's storing the bit 1, for example. In order to erase the memory, a negative gate voltage is applied, such that electrons in the electrons in the charge-shaping layer tunnel back into the channel, and the threshold voltage goes back to its original erased state. And here we can assume, for example, that it's storing the bit 0. The difference between both threshold voltages is known as the memory window, and the larger the memory window, the better the distinction between both states. Two different characteristics determine how good a memory is. These are the retention and endurance characteristics. The retention determines how long the data can be stored in the memory after being programmed. So during the retention operation, some electrons will still leak out due to the thin tunnel oxide and the built-in electric field, or due to defects in the tunnel oxide. The endurance characteristic determines how many programmed erase cycles can be applied on the memory before its performance is degraded. In fact, when applying multiple program erase cycles, due to the high electric fields across tunnel oxide, which can reach up to a few megavolts per centimeter, defects will be introduced in the tunnel oxide, which cause variations in the threshold voltage. Flash memory devices pass data in the form of binary signals. A single level cell stores 2 states, either 0 or 1, while a multi-level cell can store 4 states, for example, and each ranges for 200 millivolts with a data space or margin of 0.2 to 0.4 volts in between each range in order to keep the threshold voltage distributions from overlapping. And if the threshold voltage of the cell is within the first range, for example, we can assume that it's storing a logical state of 1, 1. And if it's in the second range, we can assume it's storing the logical 1, 0 state, and so on. For the memory to perform well, there are requirements for different layers in the device. This is a rough sketch of the energy band diagram of the flash memory. Here you see the tunnel oxide, Laquerre-Goussian, and charge-shaping layer. The tunnel oxide material has to have a hydrogen constant, which allows the use of physically thicker tunnel oxide with the same or even smaller equivalent oxide thickness of silicon dioxide. The main challenge remains in finding a high K oxide with a good interface quality with silicon. The tunnel oxide has to have a large band gap and good band offset with the silicon channel and charge-shaping layer in order to avoid charge leakage and thus improve the retention characteristic of the memory. So this means that they must have a small electron affinity. However, there is usually as the electric constant of the material is increased, the band gap is reduced. The tunnel oxide material has to be amorphous since grain boundaries in crystalline materials act as leakage path, which would deteriorate the retention of the memory. And the tunnel oxide should have a large breakdown electric field because when scaling down the devices, the electric field across the tunnel oxide drastically increases to reach several megavolts per centimeter. The tunnel oxide has to have a good interface quality with silicon, with low interfacial and bulk traps, which would otherwise cause reliability issues in the devices. So aluminum oxide is shown to have high interface quality with silicon with low bulk defects, and thus is being currently used in memory devices. To that end, I have worked on the simulation, fabrication, and characterization of memory devices using tunnel band engineering. In fact, the tunnel oxide of future memory devices would be difficult to scale down if 10 years of data retention is needed. If the tunnel oxide is made fairly thick, extended retention times can be realized, however, at the expense of high program and erase voltages and long program and erase times. Using materials with a high K for the tunnel oxide layer could be one solution. However, higher K usually mean lower or smaller band gap. So as an alternative solution is to insert multi-layers of oxides as the tunnel oxide. So in order to understand the benefits of the double layer tunnel oxide, I studied a structure that includes a silicon nitride charge-shaping layer with double layers of silicon dioxide, hafnium dioxide as tungsten oxides, and compared it to the case of a single tungsten oxide, a memory with a single tungsten oxide. So if we consider the energy band diagram of the structure, we can clearly see that the hafnium dioxide with a high K results in a much lower barrier for the trapped charges in the silicon nitride layer than in the case of the silicon dioxide. And so if hafnium dioxide is used as single tungsten oxide, the trapped electrons could more easily leak back, degrading the retention characteristic of the memory. However, using the double layer, when the applied voltage across the silicon dioxide layer is high enough, the conduction band edge of the silicon channel becomes higher than the conduction band edge of the hafnium dioxide, leading to direct tunneling across a thinner silicon dioxide layer than in the case of a single tungsten oxide, leading to a larger memory window. In addition, with the retention characteristic, studies showed that the double layer has a retention time which is slightly smaller than that of a single silicon dioxide layer. This is due to the fact that there is no larger barrier between silicon nitride and hafnium dioxide for the trapped electrons due to the higher electron affinity of hafnium dioxide. Nevertheless, we have shown that the 10 years data retention is not compromised. Now we move to the requirements of the charge shaping layer. So the charge shaping layer has to have high charge shaping density in order to allow for a large memory window. The charge shaping layer should have a high electric constant because this results in a higher electric field across tungsten oxide and thus allows to achieve the same memory window at lower operating voltages. As for the tungsten oxide, the charge shaping layer is preferred to be amorphous in order to reduce the charge leakage probability. Also, this layer should have a large band offset with the tungsten oxide and blocking oxides in order to better confine the stored charges and therefore improve the charge retention characteristic of the memory. Now that we know what are the desired material properties, the challenge remains in finding suitable materials with all the desired properties. In most cases, there is a trade-off relationship between the different properties of the material. Therefore, it is crucial to find ways to engineer and tune the properties of the materials as desired. This can be done using nanostructures or nanomaterials. For example, using quantum confinement. Quantum confinement allows us to tune the electronic properties of the material. In addition, having discrete nanostructures would enhance the retention, as only the nanostructure above a specific defect in the tungsten oxide would lose its stored charges. To this end, I have worked on the engineering of the charge shaping layer using the atomic layer deposition tool in order to grow nano islands. So the reason for using voltages, as for the tungsten oxide, the charge shaping layer is preferred to be amorphous in order to reduce the charge leakage probability. Also, this layer should have a large band offset with the tungsten oxide and blocking oxides in order to better confine the stored charges and therefore improve the charge retention characteristic of the memory. Now that we know what are the desired material properties, the challenge remains in finding suitable materials with all the desired properties. In most cases, there is a trade-off relationship between the different properties of the material. Therefore, it is crucial to find ways to engineer and tune the properties of the materials as desired. This can be done using nanostructures or nanomaterials. For example, using quantum confinement. Quantum confinement allows us to tune the electronic properties of the material. In addition, having discrete nanostructures would enhance the retention, as only the nanostructure above a specific defect in the tungsten oxide would lose its stored charges. To this end, I have worked on the engineering of the charge shaping layer using the atomic layer deposition tool in order to grow nano islands. So the reason for using nanomaterials is the possibility to tune the electronic properties based on quantum conformity effects, such that we can increase their band gap in addition to increasing their charge shaping density and thus lower the needed program raised voltage. In addition, since the tungsten blocking oxides of the memory are usually grown using the EID tool, thus being able to deposit the charge shaping layer using the same tool would reduce the time needed for fabrication. In addition, doing the deposition in a single ALD step without taking the sample out of the tool would reduce the potential contamination from the outer environment. Finally, the capability to grow nanomaterials using the ALD tool allows the conformal growth on structured devices such as FinFETs and gate-all-around FETs, as opposed to photolithography or even lithography of nanostructures, where the sidewall coverage would be difficult to achieve. So in the following, I have studied two materials, zinc oxide and zirconia, which I will be presenting in a bit. And ALD is generally used to deposit ultra-thin and uniform and conformal thin films. However, we have shown that by changing the growth conditions and the substrate termination, we can get nano-islands instead of continuous films during the first few deposition cycles following the Vollmer-Weber growth mode. The first material that I will talk about is zirconia. Zircon dioxide is chosen because it has a large charge trapping density and a high K, with large band offsets with the tunnel blocking oxides when aluminum oxide is used. The growth of the islands has been conducted on different surface terminations. So we have silicon pretties with HF, silicon with native silicon dioxide, and silicon with a thin ALD deposit aluminum oxide layer. Different growth temperatures and number of cycles were studied as well. So on the first sample, on the sample with aluminum oxide layer, which is OH terminated, hydroxyl terminated, and which is the case of the memory, we observed that with 20 AD cycles at 250 degrees Celsius, large islands which are widely dispersed are obtained. Then as the number of cycles is increased to 30, the density of islands is increased, but their size is reduced until a continuous film with a thinner thickness obtained with 40 AD cycles. On the HF Petri sample, which is H-terminated, the obtained number of islands after 20 AD cycles is higher than the case of the hydroxyl-terminated sample. With 30 AD cycles, a continuous thin film with 2.8 nanometer thickness is obtained. The reason is that the H termination acts as a surfactant that reduces the mobility of the atoms and thus results in a higher density of smaller islands. It's worth to mention that no islands were obtained at lower deposition temperatures of 150 and 200 degrees Celsius, which confirms that when the temperature of the substrate is sufficiently high, the adsorbed atoms gain the needed energy to diffuse on the surface, agglomerate, to minimize the entire energy of the system. The growth mechanism can be explained by considering the thermodynamic tendency of a full system to reduce its total energy. Surface atoms are bound less tightly and therefore they are more energetic than the bulk atoms in a specific structure. This surface free energy tends to be lowered when the surface area is reduced. As a result, the layer reduces its surface free energy by balling up into a 3D island. We have observed that as the number of islands is increased and as they get closer to each other, they tend to stretch to close the gap between them in order to reduce the surface free energy, and this results in thinner islands until a continuous thin film is obtained. The nano islands were characterized in terms of TM, which showed polycrystalline islands. Raman spectroscopy was used to determine the phase of the material, and it's found to have a cubic phase with a large Ratic constant of 35. Moreover, the band gap was extracted using the Kubalkaman function, and which showed a larger band gap than zirconia thin film due to the quantum confined effects. Were characterized. Memory devices using nano islands as the charge trapping layer have been fabricated and characterized. The memory devices are electrically characterized using high frequency CV measurements. A large memory window of 4.5 volts is achieved at a small program raised voltage of 5 volts. In fact, the high electric constant of the zirconia nano islands with cubic phase leads to a large electric field across tungsten oxide, which results in a large memory window at low operating voltages. And it is shown that the memory devices are being programmed by storing electrons in the zirconia nano islands and erased by removing these electrons from the nano islands, so there was no whole storage. This This can be explained using the energy band diagram of the memory. So the band diagram shows the formation of a deep quantum well in the nanoislands embedded in the aluminum oxide layers as a result of the conduction band offsets. This deep quantum well enables the storage of the electrons during the programming operation, while there is no quantum well resulting by the valence band offsets, which can prevent the storage of holes and cause their leakage. Lastly, to determine the charge emission mechanism in the memory, Gauss's law is used to extract the electric field across tungsten oxide, and it is shown that Fowler-Nordheim tunneling is the dominant charge emission mechanism in the memory devices. The endurance characteristic of the memory is also analyzed by conducting program erase cycles up to 10 to the 5 cycles. The measured results indicate around 13.3% of the initial stored charges are lost after 10 to the 5 cycles. The retention characteristic of the memory is also analyzed by first programming it at 5 volts and reading the state in time. The extrapolation to 10 years reveals that a 3.65 volt threshold, 3.65 volt shift in the threshold voltage, which means that around 18.8% of the initial stored electrons are lost. So this indicates that the electrons are well confined in the quantum well. Additionally, even though the zirconium ions are polycrystalline, however, the discrete islands assist in lowering the probability of charge leakage as opposed to a continuous thin film, because only the grain boundaries in the zirconia islands above the defect of the aluminum oxide tungsten oxide will add to the charge leakage. Similarly, zinc oxide nanoislands have been developed using the ALD. Using 20 ALD cycles, 3 nanometer thick islands were obtained. In this case, the thickness of the zinc oxide is comparable with the de Broglie wavelength of the electrons. As a result, quantum confinement in 1D was observed. So the nanoislands are 2D materials in this case. This was also confirmed by the extracted band gap of the nanoislands using the Kubel-Cohen function, where the band gap increased from 3.1 in the continuous 12 nanometer zinc oxide layer to 3.3 electron volts in the 3 nanometer islands. In addition, a much larger memory window was achieved with the islands compared to the case with the thin film, due to the increased density of oxygen vacancies in the islands, which are obtained due to the growth mode. I have also shown the application of the islands in solar cells in collaboration with a colleague. In this case, the islands enhance the light trapping and increase the GIC due to photon energy downshifting. So here the islands absorb the large photon energy and emit a photon with a lower energy, which then gets absorbed by the silicon solar cell and therefore enhancing the GIC. I would like to mention here that previous to my work, the ALD-based nanoislands were considered as an undesired result and were explained by having defects on the surface of the substrate or the large size of the precursors. So researchers were trying to get rid of these islands and get continuous thin films instead. My work on the intentional growth of nanoislands using the ALD tool on different substrate terminations and then characterizing them and showing that they actually have unique properties and showing their potential application in memory and solar cells was the first demonstration. Other international groups followed and used the ALD nanoislands in other applications, including single electron transistor, lasers, and photodegradation application. I have also worked on the combination, on combining both the tunnel oxide engineering and charge trapping layer engineering. In this work, iron oxide and hafnium dioxide is used as a tunnel oxide, while both graphene and silicon nanoparticles are studied as the charge trapping layer. And using quantum mechanical calculations, the program time is found to be a few nanoseconds due to the tunnel band engineering. Moreover, it's found that with graphene, only electrons are stored, while with silicon nanoparticles, both electrons and holes are being stored, which increase the program time compared to the graphene case, since the mass of holes is larger than the mass of electrons. In conclusion, we have explained that further scaling the memory devices and lowering their power consumption is becoming more difficult due to different unsolved problems. As a result, the introduction of different memory architectures or materials is crucial. In specific, the nanomaterials are promising because they allow us to tune the electronic properties as a result of quantum confound effects. We have shown that the incorporation of innovative nanomaterial combination in flash memory devices contributes to extending their scalability and reducing their operating voltage with an enhanced retention and endurance characteristics. We have also presented the growth of nanoislands using the ALD tool and explained the growth mechanism. Finally, we have shown that the ALD grown nanomaterials allow us to grow the active layers of the memory device in a single ALD step, thus reducing the contamination probability and reducing the fabrication time. With that, I would like to wrap up my talk, and thank you for listening.
Okay, let's thank Dr. Nazek El-Attab for her excellent talk. By the way, I haven't introduced myself. I'm a faculty member in Gazi University Chemical Engineering Department. So as a last talk presentation, I will present a study, PhD study of my student that has worked on composite electrocatalysis on hydrogen production, a part of his study. So in order to eliminate the risk of live broadcasting, so I would like to also present my seminar through recorded video. So I'm going to share my video through the screen also. And I'd like to apologize for the noise, background noise during my seminar. So I advise you to use your headphones during the presentation. The voice will be more clear. Thank you. Welcome. The topic I want to talk about is a study by my PhD student on PEM electrolyzers based on series support to the cathode. I'd like to give you my outline first of all. I will first of all discuss the future of hydrogen in Turkey and globally, its production by PEM electrolyzers, our method of approach for synthesis and testing of electrocatalysts, and finally I will discuss the results. Hydrogen, all we may know, is the most abundant element in the universe. It is non-toxic, highly combustible. Unfortunately, it is hidden in the form of water or hydrocarbons, which needs to be processed by mostly steam reforming or electrolysis techniques. Its main use is ammonia production, hydrocracking. Since it is non-toxic and highly combustible, it can be replaced by methane to replace greenhouse gas emissions by morphs in steel production and can be produced during gaseous peaks, during cold winters, or stored for seasonal peaks. Since hydrogen would cause no greenhouse gas, according to some researchers, we should take this chance to pass to hydrogen economy at the turning point caused by COVID-19. Therefore, we may have contributions to current policies, trying to keep 2-degree level, according to Paris Climate Agreement signed in 2015. Here in this slide gives a good comparison of the state of different hydrogen production routes. It's seen that electrolyzers have both high efficiencies and have clean production routes, and especially low temperature electrolyzers have high technology maturity level. Although high technology maturity levels seen for electrolyzers, and although high current efficiencies were observed like 67 to 74%, there are research and development efforts seen for alkaline electrolyzer, especially on catalyst membrane and efficiency. These two figures from Europe and USA show the dropping trend of the technology used to convert electricity and water to hydrogen. The paper I have shown here performed a cost review of the electrolyzer technologies from a wide variety of sources, including manufacturers, plant operators, scientific journal articles, and other reports. This paper also mentions that it's expected that wind energy will get much cheaper over time. It assumes the price of buying new wind turbines falls by 4% per year, roughly halving between now and 2030. It's also believed that renewable hydrogen might be cost competitive in countries where solar power is very cheap and abundant, like in Turkey. So renewables can be easily used to drop hydrogen production caused by electrolyzers. And among different types of electrolyzers, PEM electrolyzers can be better alternative to overcome the drawbacks of alkaline electrolyzers, whereas solid sulfate polyethylene membrane is used as an electrolyte. This polymer electrolyte membrane is responsible for providing high proton conductivity, low gas power, compact system design, and high pressure operation. On the other hand, cold acid nature regime provided by proton exchange membrane requires the use of distinct materials. This will demand the use of scarce, expensive materials and components such as noble catalysts. So the use of expensive catalysts is an issue in PEM electrolyzers. Other than being expensive, there are two main criteria for selection of cathode catalysts. So these are exchange current density and total slope. While exchange current density gives us the rate of catalytic activity, total slope gives an indication of the limiting step characteristic to different cathode materials. It's very well known that different total slopes were observed cumulatively on different transition metals from 30 to 120 millivolt per decade. So let's look at the development of cathode catalysts for hydrogen evolution reaction. In fact, hydrogen evolution studies started in 1950 with platinum metal. Further works continued on the effects of electron preparation on hydrogen evolution rate. One of the milestones was the relationship between free energy of absorption and ion exchange current density, or the volcano curve, which gives top activity metals or the potential dependent hydrogen coverage at different applied potentials. When we look at the earlier works on more than one metal catalyst, it was seen that more electronegative metals drop the hydrogen over potential drastically, and when these metals are alloyed with base metals that has lower electronegativity, same effect was observed. So it's seen from these figures that nickel has a good advantage compared to others. Other than transition metals, rare earth metals can also be used to control corrosion behavior of catalysts during hydrogen evolution. For instance, in this study, it's seen that the concentration of rare earth ions can be optimized for elimination of metal. Among rare earth metals, as a green metal, cerium sulfate exhibits good corrosion inhibition characteristics for alloy metals in acidic environments. In another work on lanthanides synthesized at different temperatures showed that nickel rare earth materials synthesized at low temperatures also offers higher hydrogen evolution rates. The electrochemical performance of nickel rare earths electrodes demonstrate that true catalytic activity is observed when rare earth elements incorporated to produce nickel-based electrodes for hydrogen evolution. Based on this overview, it's seen that since hydrogen evolution reaction mainly involves surface process and is affected by hydrogen reduction on the surface composition of catalyst type of metals alloy is a very important factor for the electrode reactions. This information may explain the paradigm of our catalyst in this study. Here in this slide, we present the steps of studies for development of hydrogen evolution catalysts. There is a preparation step which includes hydrothermal synthesis, wet impregnation, reduction of catalysts, and electrochemical and spectroscopic characterizations. In this study, in order to prepare and prepare catalysts, hydrothermal and wet impregnation techniques were used. As seen in this figure, we prepare support material for 50% cerium and 58% metal taken as a basis. Then the other steps are hydrothermal synthesis and then washing and drying in the oven. After hydrothermal synthesis, After hydrothermal synthesis, as a second step, wet impregnation step was applied. And then the reduction steps were applied at 400 degrees, 600 degrees, and 800 degrees. For electrochemical analysis of Laquerre catalysts, we have used 3-electrode system. Into our 3-electrode system, we have used platinum-risk electrode, catalyst load, and the catalyst load plus carbon-risk electrode and standard carbon electrode. Experiments were conducted in different pH acidic buffer electrolytes. Potential was controlled by a DME 600 potentiostat. Electrochemical techniques in this 3-electrode system applied for our catalysts are cyclic morphology, monoparameter, and impedance spectroscopy. Parameters used for our experiments are given in this slide. During electrochemical tests, in order to understand if the catalyst can be used for both hydrogen emulsion and hydrogen oxidation, we have immersed hydrogen into the electrolyte and scanned the catalyst at different potential rates, which you can see in the figure on the left. That on platinum, this hydrogen formed bulk can be oxidized with the scan electrode starting from the positive potential. On the other hand, scanning from negative potential will cause no difference between hydrogen purge and unpurged environments. Homemade catalysts also show somewhat similar behavior like platinum risk, but interestingly, catalysts reduced at 400 degrees exhibit high reduction occurrence compared to other reduced catalysts. This interesting behavior of we believe is due to induced activation volume of this catalyst. Here the same behavior we're also seeing for nickel series supported catalyst. When we perform thermal analysis, we have also observed the lower throttle slope in the range of 30 to 60 mV per decade for catalysts reduced at 400 degrees. After determination of surface and bulk composition by XPS and ICP techniques, we have seen that there is higher platinum, nickel, or iron at the surface compared to bulk at 400 degrees. On platinum, iron, cerium, platinum content, and nickel content drops at the surface as reduction temperature increases. Unlike iron, highest platinum content at the surface was observed at 400 degrees. In addition, on the catalyst surface oxygen was lowest at 400 degrees also. Two different patterns show after the reduction on both sides of iron, iron significantly drop and iron and platinum crystal dispersion. On platinum nickel cerium, the change in patterns is more significant after the reduction. On nickel containing support, platinum peaks significantly as rising. Reflection peaks also show it's possible to incorporate nickel into cerium. So, what does XPS and XRD say? At the sintering temperature of 400 degrees, significant changes were observed, and highest platinum content and lowest oxygen, surface oxygen was also seen. Sintering temperature significantly affects surface nickel, platinum, and iron, but not cerium. As temperature increases, platinum and nickel drops, and iron increases. Mixed cerium phase was seen at 400 degrees. Surface nickel and platinum are mostly zero-valent. Mixed cerium was also seen for platinum cerium, and platinum iron oxide, platinum cerium interactions were also observed. When we studied the effect of hydrogen purging at different pH at different sintering temperature during cyclic alternators showed that 400 degree reduced samples are activated under hydrogen purging from pH 1.1 and 2.2, giving high reduction currents. Catalytic currents in order at different conditions, we see that dominant parameters are firstly hydrogen purging, secondly the catalyst type, and thirdly the reduction temperature. As we have mentioned before, dominant catalyst type, dominant parameters catalyst type, platinum iron cerium has high platinum and iron content at the lowest oxygen level. Look at cathode currents at low potentials at -0.2 volts. We see that again the most dominant parameter is hydrogen purging and in addition reduction temperature. If you lower the negative potential mode, -0.76 volts versus standard hydrogen electrode, dominant parameters, we see that that we see is pH becomes the most dominant parameter together with hydrogen protein. In order to determine the capacitor and resistive effects, we have also performed impedance spectroscopy to the catalyst synthesized. The Galvin special polyplatin has very small impedance arc compared to other catalysts. In addition, it was also seen that in increase of reduction temperature, impedance arcs becomes bigger, which indicates higher charge transfer resistance and capacitive effects. This slide shows that at high negative potentials and lower pH values, arc radius also grows. Linear regions were observed outside the impedance arc, which indicate also diffusion of resistance. In this slide, the equivalent circuit is shown, which was used to determine kinetic parameters for electric catalyst. In this equivalent circuit, RSS solution resistance is set to constant phase element, charge transfer resistance, and volume catalyst. If we look at the effect of synthesis and experimental parameters on the charge transfer resistance, we see that reduction temperature is a dominant factor on the charge transfer kinetics, and then the pH becomes the second dominant parameter. When we look at more negative potentials, it's clearly seen that lower charge transfer resistance is mainly affected by lower pH and then the catalyst type. And finally, we have performed chronometric experiments on the predicted applied negative potentials on cyclic potentiometry at different pH and potential at different reduction temperatures. You can see on the right steady-state curves for different catalysts at different conditions. And this graph shows the order of steady-state curves from chronometric experiments at different conditions. We can say hydrogen purging has higher effect on steady-state curves at more negative potentials to lower potentials. These two potentials, first the reduction temperature and then the pH, have dominant effect on steady-state curves. As a final remark, sintering temperature greatly affects surface platinum and oxygen content. Ceria-based catalysts are composed of mixed ceria phases and nickel ceria and iron ceria interactions for earlier. And before under potential deposition by hydrogen purging, hydrogen absorbs on the surface and absorbed hydrogen can be oxidized or platinum on some catalysts at certain reduction temperatures. At different catalytic potentials, hydrogen purging is always important, leading to high reduction currents. High reduction temperatures cause higher charge transfer and capacitive effect that will be due to morphological size change. Selection of right reduction temperature and hydrogen purging is very critical for efficient catalysts and for lower charge transfer resistance. And as a final word, I'd like to emphasize the importance of hydrogen purging, and would like to give a possible mechanism about what would happen during hydrogen purging. Hydrogen purging or reduced ceria, these two steps indicate that during hydrogen purging, it will cause formation of hydrides by electron donation from oxygen vacancies, and these hydrides could be responsible for high hydrogen evolution rates. Thanks for your attention. Okay, dear audience, as a final presenter, I would like you to send your questions also through YouTube channel or in person to me also, and the other speakers. I'd like to thank you very much for your contribution and for your listening. So this is the end of this session. Have a nice conference. Thank you.